And so we get to one of the most fascinating aspects of physics, one of the fundamental forces, so to speak, for right now, gravitation. In Section 1 of Young and Freedman's University Physics, Chapter 12, but of course you'll get to gravitation no matter what physics textbook you're using. So, we can summarize it fairly quickly. What is the bottom line of gravitation, at least starting out? Of course, Einstein in 1915 came up with some crazy stuff with gravitation, but that'll have to wait for another day. The bottom line is that Isaac Newton in the 1600s, he found that the force between two masses, any two masses, doesn't matter what two masses, but that the force between any two masses was proportional to the product of their masses. That is, m1 times m2. As m1 times m2 goes up, the force goes up. That's what we mean by we say proportional to. But he also found that the force of gravitation was inversely proportional to the square of the distance between them. That means that as the distance increases, the force goes down, and it increases in relation to the square. So for every time you increase the distance by a unit squared, the force goes down accordingly. Well, how do we put that into formulaic terms? This way. This is Newton's universal law of gravitation, that the force of gravitation is equal to a constant. This is the way people used to come up with formulas. You figure out what's proportional to what, and then once you know what's proportional to what, you just have to figure out what the constant is by which you stick in front to make it equal. So proportional tells you the relationship, and then you stick a constant in front to make it exactly equal. So basically, this is the formulaic way of saying what we've already said, that the force of gravity is equal to mass 1 times mass 2 divided by the distance between the two objects squared, multiplied by some constant, g. And the constant was discovered by Henry Cavendish in the late 1700s to be basically 6.67 blah 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 times 10 to the negative 11th power. 10 to the 11th power, negative 11th power, Newton meter squared per kilogram squared. So there you have it. That's pretty much what this section is all about. There's a lot of background. There's a couple of applications, a couple of examples. They showed how Cavendish came up with this, blah, blah, blah. But that's it. This is what to memorize from this section. The force of gravity equals the gravitational constant times mass 1 times mass 2 divided by the radius or the distance between the two masses squared. Ta-da! If you have a few more brain cells open for business, here are some other items of business. So first of all, every particle of matter in the universe attracts every other particle in the universe. That may seem strange, but it's kind of a neat concept. I'm exerting gravity on this laptop. I'm exerting gravity on you, and I don't even know where you're at. You could be watching this from Mars. Probably not. But I'm exerting some minuscule, infinitesimal amount of gravity on you, no matter where you are. Every particle of matter in the universe has a attraction to every other particle in the universe. The pencil you're holding in your hand has a gravitational force on you, and you have a gravitational force on the pencil. Of course, it's pretty negligible. We don't notice it. It's very, very small. Remember that 10 to the negative 11th power thing. But you can see that when you get on the level of planets, this is why you can jump further on the moon than you can on Earth. What was that first superhero on Mars? I forget the name of that movie. It was remade, or it was made as a movie recently, where he could jump long distances. You couldn't jump that far on Mars, by the way. It's an exaggeration. But in any case, the gravitation, and this is part, the early Superman comic book, he could leap tall buildings in a single bound. He couldn't fly in the earliest Superman comic books. The idea is that the gravitational pull of Krypton was so much greater than the Earth that on Earth, Superman could leap tall buildings. But anyway, eventually we just allowed him to fly, because it is, after all, a fiction. But every particle of matter in the universe is attracting every other particle in the universe. This, by the way, explains how you can tell that you're spinning in outer space, I think. Anyway, not important right now. We calculate, so what we do is, when we're figuring out the force gravitational force on something, we calculate the superposition, or the adding up of all the forces on it. And then we vector addition them all together. And there's an example like this in my textbook. But that is the one I'm using. But again, most of the time, the force between two things is going to be pretty negligible, other than, say, the Earth. Interesting, don't confuse G, the gravitational constant, 6.67 times 10 to the negative 11th, with G, the acceleration force due to gravity. So, on the surface of the Earth, small g is 9.8 meters per second squared. That's the force of gravity on something at the Earth's surface. By the way, it goes down to 0 at the center of the Earth, gravitational force. The farther you get in the Earth, as you journey to the center of the Earth, if you could jump in a cavern, way down deep and not get burned up or whatever, you could jump farther at a certain point in the middle of the Earth, just like the Moon. And at the center, there's no gravitational force whatsoever. Of course, we can't get there. Sorry, but don't confuse G, small g, the gravitational force of something on the surface of the Earth, with G, the universal constant of gravity, 6.67, blah, 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 blah. Okay, the most important, as I've said, this gravitational force becomes most important when you get to the scale of planets. And, of course, this is why the larger a mass, the more spherical it becomes. So the Earth is spherical because it's big enough. I think Pluto is generally spherical, but once we get below the size of spherical, things get a little... when you get to asteroids or meteors, they're not quite spherical. They're kind of a glob because they're not big enough for the gravity to crunch everything in. Okay, this has pretty much been the section introducing gravitation. Gravitation is fun. Admit it, you like it.